good evening. As the president of the Finnish Physical Society, I would like to welcome you on behalf of the Society and the physics alumni of Aalto University to our jointly organized annual lecture series on the greatest physicists in history. The Finnish Physical Society is a scientific non-profit organization founded in 1947, which works actively to promote and support research, applications, and public interest in physics. The Alumni Association is an important networking organization for graduates of physics and mathematics at Aalto University. We organize these lectures together every year, and due to the pandemic, the previous two have been online only, so now we are very happy to be able to do these in a hybrid format going forward, welcoming you here in Helsinki, hello, and people around the world online on Zoom. It's not just Finland, which is very nice. This year's lecture is titled Hannes Alfvén, the Father of Plasma Physics, and will be given by Professor Emeritus Hannu Koskinen. But before I introduce him further, we'll have a few words from the Alumni Association representative.
Thank you, Daniel. And thank you for the Physical Society. So hello, everyone. My name is Raisa Lehtinen, and I'm a member of board of the physics alumni or Fysikko alumni of the Aalto University in the nearby Espoo. And I'm bringing actually greetings from our chair of board, Juha Koponen, and he was the person who was working hard with Daniel to make this event happen. We are an active alumni organization of over 300 members, and we arrange events and lectures for our members. So if you think the activity could be interesting to you, please go and check the physical.fi. And I feel that this joint lecture series is a very excellent tradition that we have had for many years with the Physical Society. So I think it's worth keeping it alive. Thank you for the organizers.
I agree completely. This is a great tradition, and we'll do it every year. Now it's my pleasure to introduce our esteemed speaker. Hannu received his PhD degree in 1985 from Uppsala University, the same university as Hannes Alfvén 53 years earlier. Hannu's PhD thesis advisor, Rolf Boström, was a student of Alfvén at the Royal Institute of Technology. After returning from Sweden, Hannu worked 10 years in space projects of the Finnish Meteorological Institute, and in 1997 he became a professor in space physics at the University of Helsinki, a position from which he retired in 2018. When Hannu was studying and working in Uppsala in the 1980s, he had the pleasure to meet Hannes Alfvén several times. In his plasma physics lectures and textbooks, Hannu usually presents the guiding center approximation for charged particle motion, introduced by Alfvén before going to statistical or fluid descriptions of plasmas. As you will soon hear, also many other concepts fathered by Alfvén have followed Hannu during his career as a space plasma physicist. So now please join me in welcoming our speaker this evening, Professor Emeritus Hannu Koskinen.
Thank you, Daniel, and I may start correct a little your pronunciation of Hannes Alfvén's name. The F is completely mute. FV in Swedish is V. Okay, I was very pleased when Daniel asked me to give this presentation, and as he said, Hannes Alfvén has really somehow followed me throughout my career as a plasma physicist. Doesn't move. Ah, that moves.
Yeah, I might be click on this, and then we should work.
Oh, great. Yeah, Hannes Olof Gösta Alfvén was born in Norrköping 30th of May 1908 as a child of Johannes Alfvén and Anna Clara Romanus. His parents were practicing physicians. His mother was one of the first female professional physicians in Sweden, and his father had also a strong interest in science. One of his uncles was perhaps the most famous Swedish classical music composer, Hugo Alfvén, another an agronomist who was very interested both in astronomy and in environmental issues, much before environmental issues became a hot topic. As a schoolboy, Hannes read a popular astronomy book written by Nicolas Camille Flammarion, which he told having strongly influenced his intellectual development and waking his passion to astrophysics. Another important inspiration was his school's radio club, where he learned how to build radio receivers. Thinking physical problems in terms of electrical circuits became later an important tool in Alfvén's approach to plasma physics. Hannes studied mathematics, experimental and theoretical physics at Uppsala University. The Department of Physics was, under the leadership of the year 1924 Nobel Prize winner Manne Siegbahn, strongly focused on spectroscopy. However, Hannes chose his early research topics in new fields, which later developed to nuclear physics and electronics. His PhD thesis in 1932 was titled Investigations of Ultrashort Electromagnetic Waves. According to Hannes himself, it was direct continuation of his earlier radio club activities. In 1933, Hannes published his first paper on cosmic radiation. Observations had shown that cosmic radiation consists of energetic particles instead of being electromagnetic radiation, but there was no explanation for their high energies. Hannes sent a brief comment to Nature in which he speculated that the cosmic rays would gain energy from collisions with larger stuff like cosmic dust, if such would fill the space. The idea was wrong, but it illustrated his boldness to propose new explanations nobody had thought before. During the next couple of years, Alfvén published several articles on laboratory electronics and alpha particles in Zeitschrift für Physik and in Nature. However, when nuclear physics became a main avenue in physics, Hannes again chose his own path and returned to the cosmic rays. In 1936, he sent another brief notice to Nature in which he proposed that magnetized double stars might act as a cosmic ray, as a cosmic cyclotron to accelerate the charged particles. In 1937, he moved to Nobel Institute in Stockholm. While he had earlier focused on the origin of the cosmic rays, he became increasingly interested in what cosmic rays tell us about the space where they move. The decay of stellar magnetic fields as inverse of the distance cubed turned out to be a problem in understanding the propagation of cosmic rays in the long distances. In 1937, Alfvén offered a new suggestion that the galaxy contained a large-scale magnetic field and that the cosmic rays move in spiral orbits in the galaxy, owing to the forces exerted by the magnetic field. But that time, space was known to be empty and could not carry currents. Consequently, the theory was dismissed, but at the end, of course, Hannes was right. He argued that interstellar magnetic fields were possible if space was filled by an electrically conducting matter, plasma, which could carry the electric currents and thus create the galactic magnetic field. And this led Alfvén to the concept of the plasma universe. Alfvén's investigations of cosmic ray propagation led him to a novel way of calculating charged particle orbits in non-trivial magnetic field configurations, now known as the guiding center approximation that Daniel already mentioned. The idea is simple. You divide the motion into two components. One is the gyro motion around the magnetic field line, called the guiding center magnetic field line, and the second is the drift of the center of that circle called guiding center. In a straight magnetic field, the guiding center may move along the magnetic field, resulting in helical orbits of the charged particles. and the curvature and gradient of the field cause the guiding center to drift perpendicular to the magnetic field. And this is nicely illustrated in this particle motion in the Earth's magnetic field, where positively charged ions drift toward the west and electrons to the east, causing a westward directed net current around the Earth. The method can be described as a perturbation theory, and it is a very powerful and useful tool, not only in space plasmas, but also in various magnetic field configurations of, for example, magnetically confined thermonuclear plasmas such as tokamaks, stellarators, ferromax, you just name it. The basic ideas of guiding center approximation were included in Alfvén's 1939 Physical Reviews paper on the motion of the cosmic rays in the interstellar space. In 1940, he published a more detailed story of the guiding center theory, including concept of magnetic mirror, particles magnetic movement as an adiabatic invariant, and diamagnetic behavior of plasma in a Swedish journal, Arkiv för matematik, astronomi och fysik. Although the guiding center approximation is sometimes called Alfvén approximation, it is curious that many plasma physicists using the approximation in their daily work do not know that it was originally Alfvén's idea. In 1937, he published his first paper on the origin of particles causing the auroras. This time he placed the accelerator in the solar atmosphere with a temporally varying magnetic field. A couple of years later, he introduced a new theory of magnetic storms and auroras, which contained a couple of that time revolutionary or heretic ideas. He submitted the paper to the leading American journal, Terrestrial Magnetism and Atmospheric Electricity, now known as the Journal of Geophysical Research. The paper was rejected on the ground that it did not agree with the theoretical calculations of that time leading authority, Sidney Chapman, and his colleagues. Alfvén was forced to publish the theory again in a Swedish journal, not readily accessible to the worldwide community, in 2 volumes of Kungliga Vetenskapsakademiens Handlingar in 1939 and 1940. He had continuous problems getting his work published in international journals. Simply, many of his ideas were too far ahead of their time. His theory contained, as I said, some heretic ideas. At the end of the 19th century, Norwegian physicist Christian Birkeland had led out a compelling case supported by theory, laboratory experiments, polar expeditions, and a chain of magnetic field observatories around the world that electric currents flowing up and down along the Earth's magnetic field in the auroral latitudes were the cause of auroras and polar magnetic disturbances. However, in 1927, the same great Sidney Chapman, who was also a very skillful mathematician, contradicted Birkeland's field-aligned currents. He developed an elegant mathematical description of the observed geomagnetic variations without these field-aligned currents. Alfvén defended Birkeland's view and based his theory on auroras really on these currents, carried by electrons and protons flowing up and down in polar regions. This led to a lifelong dispute between Alfvén and Chapman, who ridiculed Birkeland's and Alfvén's work and called Alfvén that electrical engineer from Stockholm. Note that all this happened several decades before in situ observations in space. The first direct observations of field-aligned currents were made in 1966 and originally misinterpreted as magnetohydrodynamic waves With improved magnetic field and much more extensive magnetic field observations, the existence of the currents was confirmed beyond doubt in 1974, 4 years after Chapman's death. During the early years of 1930s, Chapman had, together with Vincent Ferraro, developed a theory of magnetic storms based on the idea that huge gas clouds expelled from the sun cause perturbations in the terrestrial magnetic field, which these perturbations lead to variations of horizontal currents in the ionosphere, and these effects are then recorded on ground. Alfvén found several problems in Chapman's theory, as the gas cloud was assumed to be electrically neutral. The theory could not explain how the solar gas would interact with the magnetic field, the terrestrial magnetic field. Nor was it clear how the perturbations were then transmitted down to the ionosphere, because they didn't believe in these Wilhelmine currents. Alfvén assumed that the gas expelled from the sun was actually in the plasma state and carried solar magnetic field into the interstellar space. So the interaction between the gas coming from the sun and the magnetic field of the Earth was interaction with two different magnetic fields. And this could then drive a generator in a current circuit that is then has a load in the ionosphere. And this way also the auroras really became a natural part of the storm phenomenon. Here are some of the arguments according to Chapman, the field-aligned currents were non-physical and mathematically ugly. Yeah, they are not the solutions of equation J cross B is equal to 0 is you have kind of flux ropes which can fulfill that solution. He also opposed Alfvén's use of electrical circuits where solar plasma interaction with terrestrial magnetic field is a generator and ionospheric load, because there are no wires conducting the outer space to ionosphere. The Auroral researchers gradually accepted the existence, but the issue was not really fully settled before the satellite observations became available much later. While Alfvén could not publish his theory of magnetic storms in terrestrial magnetism and atmospheric electricity, one of his leading opponents, Thomas Cowling, was able to publish his rebuttal in the very same journal in 1942. Cowling's criticism was very much against the magnetized plasma stream from the sun. Alfvén was also correct here, although the picture became much more complete once the continuously flowing magnetized solar wind was found in the 50s. Here is just a modern picture of the very complicated and temporally evolving current systems. These red arrows are some of the currents inside the magnetosphere. In 1940, Hannes Alfvén became a professor of electromagnetic theory and electrical measurements at the Royal Institute of Technology, or KTH, or KTH, as they say in Sweden officially. He was 32 years old and had already made significant contributions to the field that later became known as plasma physics. In 1946, the chair was changed to electronics, and 1973 to plasma physics, and he built a very vigorous research community that now is known as Alfvén Laboratories. In 1942, Alfvén made his most famous discovery. He found that found a wave mode that can propagate in tenuous magnetized, fully conducting plasma, now known as Alfvén waves. This discovery was based on his special gift that allowed him to extract results of great importance and generality from specific problems. It's a mark of his genius that his initial understanding came very often from physical reasoning based on various laboratory experiments. The mathematical demonstration came only after he had, in his mind's eye, determined the physical process. Alfvén thought that it was possible to propagate electromagnetic waves in a highly conducting plasma. This, he claimed, was the easy part. Only then he developed the mathematical description. And this is the remarkably simple article. I don't think that you can read. You see only the length of the paper, which was published in 1942 in Nature. Alfvén took Ampere's, Faraday's, and Ohm's laws and added a simple hydrodynamic equation where the forces were assumed to be the Ampere's force, J equals B, and the pressure gradient. With a few simplifying assumptions, he came to a wave equation for the magnetic field. The phase velocity of the wave was given as the ratio of the magnetic field and the square root of mass density. This velocity has become known as Alfvén velocity. He made a rough estimation of the velocity in typical sunspots and concluded that it is possible that the sunspots are associated with a magnetic and mechanical disturbance proceeding as an electromagnetic hydrodynamic wave. This was the specific problem Alfvén wanted to, in this time, to investigate. Soon it was found that when also the pressure fluctuations are taken into account, another wave mode can propagate perpendicular to the magnetic field. And this is called magnetosonic or magnetoacoustic wave. And propagation is also possible in all angles between these two principal directions. However, it was well known that electromagnetic waves could penetrate only very short distance, the skin depth, into a conductor. And as the resistance of the conductor became smaller and vanishingly small, the depth of the penetration would go to zero. But Alfvén had found, by pure power of intellect, how electromagnetic waves can propagate without attenuation and reflection in a plasma of arbitrarily high conductivity. And his discovery was dismissed with remarks such as, if such waves were possible, Maxwell himself would have discovered them. Alfvén has himself told the story how the solution finally was accepted. When he discussed the magnetohydrodynamic waves 6 years later in a seminar in University of Chicago, Enrico Fermi attended the lecture. After the talk, someone asked Fermi if such waves were possible, and Fermi nodded, saying, yes, of course they are. According to Hannes, next day, the existence of the waves was accepted throughout the world. These waves were observed soon thereafter in laboratory plasma in 1949. And the same year, Fermi already used them in his theory of cosmic rays. But actually, also here, Alfvén actually was before Fermi. But Fermi, okay, he certainly deserved the fame of this. Alfvén waves form a much richer family of plasma oscillations than anticipated in the 1940s. They are the primary mode of information transport in magnetized plasmas everywhere, from laboratories to astrophysical plasmas, that is, everywhere in the plasma universe. For example, the entire Earth's magnetosphere or planetary magnetospheres, they oscillate as ultra low frequency, very long wavelength magnetohydrodynamic waves. The discovery of this wave mode actually was the birth of magnetohydrodynamics, which during the coming decades became a major tool in thermonuclear research, in solar and stellar physics, and in studies of planetary magnetospheres. In this context, Alfvén introduced the concept of magnetic field frozen in the plasma flow. That is a picture where the magnetic field lines move like spaghetti together with the plasma. It turned out to be very powerful tool in domains where the ideal MHC assumptions are valid. That means where the resistivity is negligible. But problems started popping up when the frozen in flow breaks and the magnetic fields are rearranged in a process called magnetic reconnection. Reconnection was first proposed to explain the solar flares in late 1940s, and in 1960s it became a standard description of energy transfer from the solar wind to the magnetosphere, and also breaking of the configuration in the night side magnetosphere leading to auroral breakups. At this point, Alfvén denounced his own concept of frozen fields as pseudo-pedagogical, meaning it gives you an impression that you have understood a physical phenomenon, but you have in fact badly misunderstood it. Alfvén pointed out that the magnetic field lines are not spaghetti-like physical objects that move in space. They just give the direction of the magnetic field in a point of space at a given time. It is true that if two plasma elements are connected magnetically to each other, they remain so as long as this assumption of negligible resistivity holds. And this connection breaks in the reconnection process. But then this studying it requires addition of resistance or consideration of smaller scale kinetic effects. The Nobel Prize winner of 1948, Patrick Blackett, has been told to tell to his students, electromagnetism is difficult, hydrodynamics is very difficult, but magnetohydrodynamics is damn difficult. I used to refer in my lectures the classical plasma physics textbook of Kroll and Trivelpies. The fluid theory, though of great practical use, relies heavily on the cunning of its user. Alfvén himself was very cunning. In 1950, he collected his early contributions into a monograph, Cosmical Electrodynamics. A scanned copy of this book can be downloaded from Internet Archive as a very poor quality PDF file. But it's interesting to see. I here only display the table of contents because this is quite typical to Alfvén's approach. He does not present a complete physical theory from elements to applications. Instead, he selects several problems to which he applies electrodynamics and magnetohydrodynamics. The latter of which in that time was still in its infancy. A thoroughly revised edition of this book with together with Carl Gunnar Feldhammer was published in 1963. It's more modern and much easier to read, although the physics remains damn difficult. Alfvén's main interest started moving towards the formation of the solar system in 1940s. He had found the concept of critical ionization velocity. It's a very simple idea. Once relative velocity of neutral gas and plasma exceeds, or the energy calculated from that relative velocity exceeds the ionization energy of the neutrals, they start to ionize. And this ionization continues as long as, and it limits the ionization limits the velocity of the neutral gas, and this continues until very high degree of ionization is achieved. Alfvén speculated that this process was very important in the interplay between plasma state and neutral state in the formation of planetary systems. Alfvén's intuition was certainly right concerning the critical ionization velocity, which was soon demonstrated in laboratory experiments. How important the phenomenon is to the formation of the solar system is, however, another question. Another example where Alfvén was ahead of others. He predicted in 1950, together with Nikolai Heroldsson, the existence of non-thermal synchrotron radiation from strong magnetic fields in the galaxy, before those guys whom it is often addressed. As so often, he got his idea from laboratory experiments, this time naturally from particle accelerators, cyclotron and synchrotrons. So then, Ludwig Biermann had, in 1950s, he found that comets have two tails. One is formed by the outflow of neutral dust pushed away by the solar radiation pressure. This outflow is low and becomes aberrated when the comet goes around the sun. The second tail is directed almost radially away from the sun, indicating that it consists of particles moving much faster. Because the fast tail is always seen when it is bright enough to observe, Biermann concluded that there must be a continuous fast corpuscular flow from the sun. That flow is the solar wind. Recall that the early theories of magnetic storms of both Chapman and Alfvén had assumed only intermittent gas clouds, intermittent outbursts of gas or plasma clouds. To Alfvén, it was immediately clear that this solar wind would be highly ionized plasma carrying magnetic field. And in 1957, he explained that the plasma tail is formed when the solar wind magnetic field picks up newly ionized particles from the coma of the comet. The ionization of the particles is through solar ultraviolet radiation. And then back to the magnetic storms. Alfvén continued to refine his theory of magnetic storms and auroras through the 40s and the 50s. His landmark paper was published in 1958 in Tellus. Alfvén wrote in the acknowledgements of this paper, "I wish to thank Professor Cowling for discussions and correspondence. His criticism has helped me to clarify the ideas and develop the theory. This does by no means imply that Professor Cowling accepts the theory even in its present form." This is a very good example of Alfvén's wit. He had a lot of this kind of comments. This theory included a formation of potential difference between the outer magnetosphere and auroral ionosphere. The idea, Hannes got the idea from laboratory experiments of electric double layers in gas discharges. In the auroral zone, the potential drop, or if you want to say so, double layer is of the order of 10 kilovolts, which was later observed as a corresponding peak in spectra of electrons precipitating to the atmosphere. The picture on the right is a sketch of the modern view of large-scale potential structures, and this has been verified by several satellites crossing that region. In this context, I ask that you allow a little ego trip. The small-scale details of the potential drop remained unclear until 1980s. Observations of an American military satellite suggested that already in the late 1970s that the potential drop would organize as several weak double layers on top of each other. The amount of relevant data was very limited, as was the instrumentation of that satellite. In 1986, we had the first Swedish scientific satellite Viking in the sky, and detailed study of these weak double layers was one of the goals of the instrument in which I was participating in Uppsala. Viking had much better instrument. It produced much more observations than the mentioned American military spacecraft. Here are a couple of reproductions of our very initial analysis in the spring of 1986, including my own handwriting, which at that time was still readable. During the lifetime of Viking, we observed hundreds of these weak double layers and published a comprehensive analysis of their properties in a very well-cited articles in Physical Review Letters in 1988. The weak double layers turned out to be small upward flowing ion holes, or holes in ion density, with a potential drop of less than 2 volts, mostly less than 1 volt over each. Now, in the summer of 1986, Hannes Alfvén had again migrated to Sweden, and he came to visit the Viking Science Center in Kiruna, where I happened to be sitting and analyzing our observations. I knew him already before, and I felt very honored to be able to show him data like these. After all, he was the father of parallel electric fields. No, he said a few very friendly words, as he used to do, but I understood that this didn't anymore interest him at all. His mind was occupied by the urgency to explain the Saturnian rings. The discovery of by James van Allen and his group of that the Earth is surrounded by belts of energetic electrons and protons trapped in the geomagnetic field came with the first American satellite, Explorer 1, in 1958. It was a surprise to many, but not at all to Hannes Alfvén. He was quick to discuss the properties of the particle spectra already at the time when the radiation was observed only using simple Geiger-Müller tubes. The existence and dynamics of these Van Allen radiation belts is something where the guiding center approximation is extremely useful even today, when the individual particle orbits can of course be directly computed using normal laptops. In 1960s, Alfvén intensified his efforts to understand the entire plasma universe. According to him, there was no rational reason to doubt that the universe has existed for an infinite time. The Big Bang was for him only a myth that attempts to tell how the universe came to be either 6,000 or 20 billion years ago. Alfvén's opinion was that Big Bang cosmology is just the result of abuse of general relativity by mathematicians. Note that he had nothing against the relativity theory itself. On the other hand, Alfvén did not accept at that time rather popular steady-state cosmology either, because it required continuous creation of matter, and Alfvén was against any idea of creation of or a creator. Thus, he came to dispute also with Fred Hoyle and company. He advocated another model known as Klein-Alfvén or Alfvén-Klein cosmology, which was based on his former teacher's Oscar Klein's idea of large-scale matter-antimatter symmetry in the universe. The domains of matter and antimatter would be separated by electromagnetic fields, but in case they would come to contact, huge amounts of energy would be released, explaining the greatest detected energy bursts. Lev Landau has said, the cosmologists are often wrong, but never in doubt. Perhaps Hannes was one of these guys, but he was in very good company. Then, 1970 came the big prize for fundamental work and discoveries in magnetohydrodynamics with fruitful applications in different parts of plasma physics. Considering the contributions that I have described and many more that I have not been able to cover in this lecture, the prize certainly was well earned. Hannes Alfvén was throughout his life engaged in environmental and societal issues. After the Second World War, he supported nuclear energy production, but in the 1960s, he converted to a strong critic of fission-based energy production due to the environmental problems of nuclear waste. He also criticized too weak investments in research of peaceful use of thermonuclear energy. This led him to a total conflict with Swedish authorities, and in 1967 he noted that his work was no longer desired in Sweden. After this, he immediately got offers both from the Soviet Union and the USA. He spent first a couple of months in Soviet Union, but decided to move to California and accepted a professorship in University of California, San Diego, La Jolla. He kept his chair at KTH and started a life of a migratory bird, moving around the vernal equinox from California to Stockholm and autumnal equinox back to California. The fight with Swedish energy authorities continued. In the 1970s, Alfvén was active in the Swedish Center Party. In a party congress in 1973, that time with the authority of a Nobel laureate, he gave an emotional speech against nuclear power, which may have been an important step toward the later political decision to stop nuclear power production in Sweden. Different deadlines have been given to it, but as we all know, it hasn't been completed yet, 50 years after Hannes' talk. Later, Alfvén became a supporter of the Green Party, and in 1980 he left his position in the Royal Swedish Academy of Engineering Sciences as a protest of its nuclear energy policy. He was a productive scientist. The list of more than 300 entries in ADS database is not quite complete, as some of the important early articles published in Swedish periodicals are not indexed there. It's notable that he wrote almost all of his papers as a single author, although he often acknowledged, of course, discussions with his colleagues. Furthermore, he did not claim co-authorship if he only had given the idea of the work and discussed with the author. Acknowledgement was enough for him. In my mind, many of the most important papers from the Stockholm group were so strongly influenced by him, both before and after he started the equinox migrations, that he could easily have been counted as a co-author. In addition to scientific monographs, He wrote a couple of more philosophical books, one of them together with his wife Kerstin, and even one science fiction using pseudonym Olof Johannesson. Olof was Hannes' second name, and he was a son of Johannes. As a person, he was very multi-talented. He spoke several languages, Swedish, English, German, French, and Russian fluently, as well as some Chinese and Spanish. He had wide cultural interests, studying history of science, Oriental philosophy, and religion. But he was irreligious and very critical toward all religions. In addition to his engagement in questions of nuclear power, he was active also in the book was peace movement. I think he was even chairman of that group sometime. Although he had during his long life a lot of scientific and political battles, his private life was very peaceful. His marriage with Kerstin Eriksson lasted 57 years until her death, and they raised 5 kids. He was very hospitable to his friends. I have heard several stories of great beach parties in California. He had an excellent sense of humor and could come up with quick anecdotes on all matters. He was generous to young scientists, of which I also benefited during those perhaps half a dozen occasions when I met him personally. He continued to be occupied by the solar system formation and his criticism of Big Bang cosmology until his very last years. While he probably was, just like other cosmologists, often wrong, we must remember the great physicists of what they accomplished, not what they did not accomplish. He stopped migrating between La Jolla and Stockholm in 1988 and settled in Sweden. He passed away on 2nd of April 1995 in Djursholm near Stockholm. This picture with a warm look and gentle smile is an excellent representation of the great man as I remember him. Thank you.
Are there any questions for Daniel? On Zoom or in the room? I'll bring the sheet. Okay, then I'll start. I have something to go. I'll write them down. In your opinion, what lessons are there to be learned for early career scientists and his identified early
Never give up. I think that is perhaps the most important. I don't. Today's publication environment is rather different, and you have probably more choices where to put your article. But it's clear that if you meet a kind of this kind of arguments that if that were so, Maxwell would already have found it, or this must be wrong because it doesn't. It is not consistent with some very high authority. You should never accept those arguments per se. But of course, if your calculations are wrong, then you have to correct them. And actually, Alfvén kept on correcting his ideas throughout his career. For example, this cosmic ray stuff. He started with a couple of these collisions with neutral stuff was clearly wrong. Then it was of course the particles are the cosmic rays are accelerated in the very high magnetic fields, and then he realized that there must be magnetic field all over, and then he added little more and more. And the same with the storm theory, that in the beginning it was certainly incomplete. Then he added it a little. He published several papers where he improved the theory, and finally he was found to be right. But of course, it's a little bit. I find it a little bit dangerous that we compare ourselves too much with these people with somehow special intelligence. We are just ordinary people.
Okay, thank you. Any other questions?
Okay. Thank you, Anno. It was a very fascinating story, and definitely like his career spans many different channels. I just one thing I was just wondering when I was listening, how was it like for a Nordic country scientist in 1930s, 1940s? What kind of interaction was able to be with him? Like you mentioned, he had a bit these controversies and had a bit maybe trouble getting his ideas always accepted. And he mentioned he met Helmut in 1948, but before that, how much traveling, how much visits and
I don't know how much Alfvén traveled that time. Of course, and at that time the travels were often so that, for example, if you went to the United States, you visited that on the same trip several different places. And he had colleagues and friends and enemies all over the world. But in the 30s, for example, the Nordic science was very, and physics was relatively small. In Sweden there were, but for example in Finland, we didn't have too many people with whom he could even talk. But in Sweden there were. But for example in Uppsala at that time, the only thing they were really concerned of was spectroscopy. So if there is a man who wants to do it his way, you are a little bit outsider very long time. But later, when he was at the point when he started these migrations between California and Sweden, yeah, there were already lots of contacts and he. So, but it's difficult to know how it was in 30s. And actually, I asked once Carl Gunnar Feldhammer, who is the most important, or has been the most important advocator of Hannes Alfvén, how was the paper sent from Stockholm to London in 1942? And he didn't know. So it was wartime, but somehow there was an envelope that was carried from Sweden to Stockholm, middle of the Second World War. There was no fax or email.
Okay, why was the stark differences from the 50s and 60s between American education publications and European education publications?
Honestly, I don't know. It's beyond my expertise. 50s and 60s, of course, the American science leaped away from the European very much, thanks to the Manhattan Project and everything. So, and all those guys who moved from Germany to the US, so that suddenly their scientific community became much bigger and much stronger than we had in Europe at that time. Although there were, of course, good scientists left in Europe as well. But difficult to compare, at least for me.
What was behind this leadership against Hitler? What's the reason why?
He thought that it was just a just he thought that the problem was that it happened limited time ago. So somehow, so he connected it in his head to creation, and he didn't accept any theory of creation. Of course, we don't know what happened before Big Bang. In a sense, perhaps the present understanding of Big Bang is not that everything started 13.8 billion years ago. What was before that, we don't have any clue. But he was. But then there was, of course, this that while he fully seems to have fully accepted general relativity as a theory and construction, we know that it leads to singularities. And he thought that there cannot be singularities in physics. And if you kind of extend your theory to the singularity, then you are a little bit in trouble. What is there in the singularity of black hole? Of course, black holes exist, but what is there inside? We don't know. So his opposition was that, and then of course he had in a very young age got this idea of matter-antimatter symmetry, which is not a part of Big Bang cosmology. So for him, the universe was eternal, evolving, but different parts of the universe can evolve differently, and we do not necessarily have any data from so far. But as I said, he probably was one of these cosmologists that was wrong, but he's not the only one.
One more question. It looks like in the chat this isn't working.
Okay. So.
Yeah, maybe this like this historical kind of arches we are painting here. So one more in that area. What is the contribution of Alfvén on Finnish space science? And we obviously see like his student here. And was it somehow activating or bringing forward the field in Finland at Helsinki or FMI or and so on?
Indirectly, because many of us studied, or some of us at least studied in Sweden, and there was the Alfvén's influence. And of course, because auroras have always been important research topic in Finland well before, since from the 19th century. So it is that this, for example, Birkeland's ideas of Finland currents were well known in Finland a long time, already before they had been observed, and the Finnish aurora researchers applied this concept without any difficulties. So in this sense, and certainly Alfvén's work was well known, but actually I don't even know if he ever visited Finland. No, I'm not sure. Oh.
Okay, then I think we'll thank our speaker again. And thank you for joining us for this Greatest Physicists in History lecture. There'll be another one next year. Hopefully see you there. And for the people in the room, there will be sparkling wine in the first floor lobby. So hopefully see you there to discuss more with the speaker. Thank you.
Thank you.